In this lesson, we're going to study logarithmic differentiation. We're actually going to be differentiating things that we could have differentiated before using product and quotient and chain rule, but this is going to make it a little simpler. Sometimes it's a pain to use the product rule and quotient rule, especially when there's a lot of products and quotients involved. So what we're going to do is we're going to go ahead and take the natural log of both sides and use the rules of logarithms to change these products into sums and the quotients into differences. And so then we'll just be differentiating natural log, which find the derivative of natural log is much easier than finding the derivative of products and quotients. So let's go ahead and try it with this one, which wouldn't be too hard using the quotient rule and the chain rule, but we're going to look at this using this logarithmic differentiation. So the first thing we're going to do is we're going to take the natural log of both sides. We have the natural log of a quotient, which means we can do the natural log of the top minus the natural log of the bottom. At the same time, we have these powers, and we can use the power rule. The 2 can come out front, and the 4 can come out front. So we're going to differentiate here. The differential of y is just 1 over y dy. Over on the right side, we got 2 times the differential of natural log of x, which is just 1 over x. For this one, we have to be careful. We have the 4 in the numerator, and this is going to be 1 over 3x plus 2, but we also have to take the derivative of what's inside. So we still do have to use the chain rule. So the derivative of 3x plus 2 is just 3, and that's where this 3 comes from right here. We want to solve for dy dx because that's the derivative of this original function. So we divide both sides by dx, and we multiply both sides by y. So that's what we get here, but when we find the derivative of something, we don't want y, or the original function, in our answer, but we know from up here that y is just x squared over 3x plus 2 to the 4th. So we're just going to substitute that back in for y, which gives us this answer here, and this is the answer to what is dy dx. So we found the derivative of this, not using the quotient rule, but changing to logarithms, find the derivative of our logarithms, and then substitute back in for y. And all of these are going to be similar. They're going to get a little bit complex as we work through these. So here's another one. Again, this would be a pain because we have a product rule, some chain rules, a quotient rule. So what we're going to do is take the natural log of both sides, split it up using the rules of logarithms. So this would give us a 3 natural log of x. Remember, the square root of x squared plus 1 is really x squared plus 1 to the 1/2, so we're going to use that. And so here's our first one, 3 natural log of x. Secondly, we have the 1/2 comes out front from the square root, natural log of x squared plus 1, and then minus, because it's division, natural log of x plus 2, but the 6 comes out front, so that's why we have that 6 there. Now we can find the derivative. On the left, we have 1 over y dy. On the right, we differentiate 3. The derivative of natural log of x is just 1 over x. Here we have our 1/2, and that's why we have our 2 here to start with. The derivative of natural log of this is just 1 over the x squared plus 1. That's where that comes from, times the derivative of what's inside, so 2x, and that's why that's in the numerator. And then the derivative of this is just 6 over x plus 2. To do the chain rule there, the derivative of x plus 2 is just 1, so that doesn't affect anything. Now we're going to solve for dy dx. So I divided both sides by dx and multiplied both sides by y. We can clean this up a little bit by, first of all, plugging y back in for y, and then we can reduce a 2 here, which will make things more simplified. So I plugged y back in, and actually I multiplied this 2 out instead of reducing. Reducing actually would have been better. Our last one here looks like it got cut off a little bit. I still think it's visible, so here we go. A very complicated one, a few products, a quotient, and several powers. So we're going to take the natural log of both sides. Looking at our next one here, it did get a little cut off, but I think it will be okay. This one's very complicated. It would be very complicated to use the product rule and quotient rule for sure. So we're going to go ahead and take the natural log of both sides. Once we take the natural log of both sides, we can rewrite this right side with sums and differences, and we'll also use our power rule to bring any powers like 4 and 2 and 5, and this is to the 1/2 power. We'll bring those out front. So we have the 1/2 natural log of 3x plus 2 plus, since it was multiplication, we add, the 4 comes out front, and then natural log of x cubed plus 1 plus, we could still multiplication, bring the 2 out front, and you get natural log of 5x minus 3, and then we're going to subtract, because it's all divided by this part. The 5 comes out front, and natural log of x cubed minus 2. Now we're going to go ahead and differentiate each term. The left side is just 1 over y dy. The right side, taking the derivative of natural logs, puts this part in the denominator. We just can't forget to use the chain rule. So that's where the 3 comes in the numerator here. We have 4 in the numerator, 1 over this, so that's why x cubed plus 1 is in the denominator, and the derivative of what's inside is 3x squared. Our next term, we have the 2 in the numerator, natural log of this, so that's 5x minus 3 in the denominator, times the derivative of what's inside, gives us this 5 right here. And the last one, we have subtraction. The 5 is in the numerator. X cubed minus 2 is in the denominator, and then chain rule, derivative of that is 3x squared. We're going to go ahead and divide both sides by dx to get dy dx. Multiply both sides by y, and I'm going to go ahead and substitute the y in at the same time. So I'm going to put this back in for y, and we get our answer. So didn't take us too long. Would have been very, very complicated using the product rule and quotient rule. We have a couple more examples of ones that are going to be better to find the derivative using this logarithmic differentiation. So here we have an interesting function, y equals x to the x, and we want to find the derivative of that. So once again, we're going to take the natural log of both sides and use the power rule, brought the x out front. And we're going to go ahead and take the derivative of each side, realizing that on the right side we do have a product, so we still will need to use the product rule. It will be simple though, so we've got our dy over y. The previous ones I wrote that as 1 over y dy, but it can be written as like this. Product rule, we got first times the derivative of the second plus the second times the derivative of the first. We have some canceling that can happen here, and getting dy dx, so I divided both sides by dx, multiplied both sides by y, and now we can substitute back in. Instead of having y, we know that y is really just equal to x to the x. And so our answer is x to the x times 1 plus the natural log of x. Our last example, similar to the last one, except that we have a function here in the exponent. So we're going to go ahead and take the natural log of both sides, bringing our power out front using the power rule. And again, we have a product rule. On the left, dy over y. On the right, we have first times the derivative of the second, which is 1 over x, plus the second times the derivative of the first. Doing some simplifying here or multiplying, we get this. I divided both sides by dx, multiplied both sides by y. Notice here I have a fraction, and this x can go to, this is a common denominator, so we can have an x cubed over x plus a 4 over x, which will simplify. Can plug back in for y, and so that x cubed over x is x squared plus the 4 over x, and then 3x squared times the natural log of x. And that's using logarithmic differentiation. It makes difficult functions involving multiplication and division a lot simpler rather than using product and quotient rule.